afternoon. So as he just said, I'm not going to claim that I'm any expert in deep learning, but I'm very interested in it, and I probably want to learn about it as much as everyone here. So if you are an expert in Bayesian deep learning, this is not the venue for you, because you are probably way above what I know about deep learning. But however, I do know a bit about Bayes. I'm a lecturer in the Department of Statistics at the University of Pretoria, but I'm a mathematician by training, so I've got a little bit of a combination of both of them. So when they asked me if I could come talk, I freaked out for a little bit, because I thought, but I don't actually know any intricacies of deep learning, but I do know some statistics. So I thought maybe the more statistics I know, I could pass over to some of you. Right. So this is sort of my outline. Just to warn you in advance, I have an horrendous cough. So if I start coughing, it might sound like I'm dying. I'm not sick at all. There's no bugs. But it's going to sound bad, right? Just so that you know. It's my warning. Right, so I'm first just going to give a very one slide on neural networks, which will be my level of what I sort of know about neural networks. How you bring the Bayes in, because obviously this is an important thing, and why I believe that Bayesian neural networks is the way to go. Okay, being a statistician, I would obviously be biased towards that, but I have good reasons for it. And then I'm going to look at first, classical parameter estimation, which I think we should all feel a bit comfortable with, but I'll just do a sort of recap in case it's very long ago and we're really not comfortable with it. Then I will show what Bayesian estimation is. So this is in the normal estimation setting, nothing to do with neural networks. And the classic coin flipping example for Bayes estimation. And then I'll talk a little bit about the normal distribution and why it's not usually my first choice, right? Not only in deep learning, but in other areas as well. And then what do we do with Bayes computationally, which I'm also not an expert in, but obviously these are all things that are available in software that we can easily apply. So to start off with, just to make sure that everyone knows I'm a statistician, is statistics can be made to prove anything, even the truth. Okay, and my husband is an actuary, and you would think that he would believe in a bit of statistics, but he really doesn't. So every day I get comments like this, and I'm like, I'm still a statistician, and I believe in what statistics can do, etc. So and I actually Googled, and I wanted to find nice quotes about statistics on the internet. They are not there. I searched through about 3 or 4 pages of Google, and I was like, why? Why are they not there? So I would find, well, I'll just resign myself to the fact that people believe statistics is mad. Right. So, but however, and this is the most famous one, there are lies, damned lies in statistics. Okay, I claim that, and I tell my students this very, very often, the more you study, the more you realize you don't know. Okay, so a first-year student is the most dangerous academic on the planet, right? Because they believe they've come from high school and they've probably got straight A's for everything. They believe they are super, super clever, right? And they're not intelligent, but they don't know anything because they don't know what they don't know yet. And the more you do research and the further you study, and when you finished your PhD and you carry on, you get more and more humbled, and you realize what you don't know. And I think that is a massive advantage, because you tackle a problem with an open mind. You don't go one-tracked into it. You believe that there are other ways to do it, etc. So, and I think that's what happens with statistics, because practically everyone with a BSc or BCom will do a first-year course in statistics, and then we're all experts. Okay, we are by far experts with one course of statistics. There are so many levels of statistics that you learn later on, that you do in postgrad studies, and many degrees miss out on that. Okay, and obviously it's not possible for everyone to major in everything. That we have to be realistic. But I think statistics is based on this type of quote that just goes everywhere, all over the internet. We have to just be a little bit open-minded and realize that statistics looks like this because you don't understand statistics. Okay? So I'd like to, and granted it's very complicated and massive, and there's all sorts of branches of it, so none of us can be an expert, and I am no expert. I don't know all the branches of statistics, especially because I'm actually trained as a mathematician, so I don't have master's level statistics. I have mathematician, but I've obviously I'm exposed to it when I teach. I do teach high level statistics courses. But as long as you know that there are other ways to do something, and you know that in statistics you have to check your assumptions, what can you do, what you can't do, then I think you're starting to go on the right track. So this is obviously a very bad quote, so please, if you see it, scribble on it, scratch it out, it's a lie. Okay. Am I going backwards? Okay. So facts are stubborn and statistics are more pliable. So I chose this one because of the deep learning context. When you do a neural network without statistics, you are getting a fact out at the end, which is fine. There's nothing wrong with it, and there are models that work very well. But when you put in uncertainty and you try and model the uncertainty, you have much more information. You have expected values, you have variance, you can make an informed decision as opposed to just a single outcome, and that is the advantage. And that is also the difference between the classical parameter estimation versus Bayes parameter estimation, and that's why I wanted to start with that. All right, so I think this is the most common picture of a neural network on the planet, not mine, it's Google's, or whoever put it on Google. So a neural network is a cascade of multiple layers of nonlinear processing units for feature extraction, and obviously there's many versions of it and complications and different layers. But basically, and this is my level of what I understand, so you feel free to chirp in and add comments if you want. Each neuron is a placeholder, and we activate it, and obviously we train it so that what our input goes through the model and we get something out, right? And that's very, very simple situation. And it's all about training this, right? And that's where all the mathematics comes in. Now when you go to Bayesian networks, instead of wanting a single value out there, this is the answer. I allow for uncertainty in my weights, the things that I have to train, instead of just a specific value that I want out. So I train for one value, I train for a distribution for it, so I have uncertainty, so I know which weight is maybe causing most of the issues, etc. And then I have a probabilistic output instead of a deterministic. Okay, and I really, as I said just now, believe that this is a much better way to do everything in life. Because I come from a mathematics background, when I was taught undergrad and into my postgrad, we do mathematical modeling, and it's always deterministic. Okay, and the Department of Mathematics at the University of Pretoria does biomathematics, so they have a lot of disease modeling things. But they're not statisticians, so they do a little bit of stochastic modeling, but it's mostly deterministic. Okay, and that's quite difficult. A disease has high uncertainty in it. How does it spread? Who has contact with who? And so that's just one example of how you should bring in statistics or probability to models. Okay. So Bayesian deep learning allows for distributions of the weights via prior distribution. So prior is exactly what it sounds like. It's a good name for it. What do we know already? Before we've tried to model anything or train anything, what do we already know? Right. And then while I was looking at stuff, and this made me really confident on why this is very important. Last year at NIPS, there was actually a whole workshop on Bayesian deep learning. So I'm pretty sure this is a big thing. Okay. Right, so Bayesian deep learning or Bayesian neural networks, sorry for that terrible spelling there. Traditional, goodness. Okay, so traditional deep learning cannot represent the uncertainty. Okay, so how much confidence do I see in the outcome? You just get an output, and obviously as the user you can, make certain remarks on it. But if you have something with a probability distribution, you have a quantifiable uncertainty measure, right? It's also more robust to overfitting. And the prior distribution provides a range for the weights. Okay, and that's the first thing. When you're trying to decide on your prior distribution, and when I get to the normal distribution later, that's one of the things I want to touch on. You choose a range. Okay, and almost everywhere people use a normal distribution, and not just in deep learning, everywhere. Everyone's like assume it's normal. Almost nothing is normally distributed. Okay, and if you just plot it, you would see that. Okay, I actually had a consultation project once with a prof from, I can't remember what department, but I was helping his PhD students, and he wanted to fit a certain statistical model. And of course, as a statistician, I went and checked all the assumptions, and it was so highly non-normal, this model couldn't work. And I told him, I said, sorry, Prof, we can't use this, but I have an alternative for you. It will work very well, and I think it will actually work better because you can talk about the output better with whoever you want to present this to. Yes, and he was so upset he didn't talk to me and the student for 6 months. And I was like, don't come to me if you don't want me to check the things. Okay, so stuff is almost never normal. So, and of course people use the normal because you have the law of large numbers and everything sort of averages out and it turns out fine, but there's much, much better choices. So I will later just touch on that a little bit. Okay, And then the posterior distribution is the afterwards one, okay? And that's what we once we've done all our Bayes. And I'm actually going to do, in this talk, some little calculations, all right? So if you want to follow with me, I'll go slow enough. I like to do calculations, so you'll get them. All right, so classical parameter estimation. This we should all know. Okay, who's never heard of maximum likelihood estimation? Very good. Method of moment estimation. Oh, wonderful. Okay, so it's all good. So this is what we taught when we first used statistics. The maximum likelihood estimation, method of moments, and there's also method of percentiles, but these two are very similar. Maximum likelihood is the most common one. And in words, don't try and memorize it as an algorithm, memorize it in words. What is the likelihood I observe what I observe? And what is the maximum of that? That gives me my parameter. So our likelihood is what is the likelihood, the probability that I observe that given so the x underscore is my given data, right? I'll use that throughout. And theta is the parameter we don't know. So what is the likelihood I observe that given the theta is whatever? And to solve that, you take the derivative, set it equal to 0. And obviously often we often take log of that because the derivatives are much easier, etc. So that's maximum likelihood estimation. Fine, you can get a theta hat estimate, right? And it works well in most cases, right? Method of moments is much simpler. Both of them, of course, assume that you have a distribution. You've assumed that the x's come from a normal. It assumes it comes from a beta or whatever. So that when you build that likelihood, you've got the beta functional form in there. The same with method of moments. You take the theoretical formula for the expected value. So for the normal distribution, it's just mu. Or you take the theoretical distribution for the beta and you plug it in there. And then you take your sample data, you calculate the sum of xi over n, and you set them equal. If there's just one parameter, you just need one equation. If there's more, you go to the second non-central moment and you carry on until you've got enough equations for the number of unknowns. Okay? All fine, as long as you have nice theoretical formulas. Okay? And they don't behave badly, except that for some distributions, you might find that these two will differ, or it's not stable, or it's very sensitive to sample size and things like that. Okay? But with all techniques, there's always some disadvantages somewhere, right? But the big disadvantage here is that it's just a single value. You can obviously in some cases work out the distribution of the theta, the estimate, there's theory for that. But Bayesian estimation just combines everything all together and it's just much more logical. Method of percentiles is very similar. It sets the 25th percentile to the theoretical 25th percentile. But then you really have to have the functional form of the CDF or the PDF. Okay, and you get however many equations you want. Right, then Bayes estimation. This is just a summary, and then I'll do some nice mathematics afterwards. You've got your data from wherever you're observing it from. It comes from some distribution. So you do also need to know the functional form of that. But, I mean, if you plot it and you see it's not normal, software nowadays, you can try and fit all sorts of things and you'll find the distribution. So that's not a big issue. Unless it's very complicated and it's bimodal or something like that, you've got some opportunities to do that. But what's important here is the parameter theta is unknown. Okay, so I'm really looking at the simple case when we have one parameter. Okay, in deep learning, we're obviously super more complicated. We want an estimate for theta. Right? So you could do, like we did on the previous slide, do maximum likelihood estimation, method of moments. But what if we know something about theta? Okay, when we're here, we're not assuming anything about theta. All we say it's a parameter. It might be it's most likely going to be the location parameter of the distribution, but that's all we know. Right? And we don't, even if we do know something else about it, we don't include it in our calculations. We don't use it to our advantage. So Bayesian estimation says we treat this as a random variable. Right? So that's the big fundamental difference between classical and Bayesian estimation, and we give it a distribution which we call the prior. Okay? So it sounds like it's just one thing, but there's a number of things underneath there. Number one, we're giving it a range. So we believe it's always between 0 and 1. That's great. We have already some information. In maximum likelihood, we don't use that anywhere. Okay? We just hope that the formulas that we use will pull it through like that. Okay? But if it's not, if it violates something like that, what do you do? Right? So here you can make sure that those sort of assumptions are valid. Then, so let's assume we're looking at a parameter between 0 and 1. Do that all we know? Then it would have to be a uniform distribution, so we don't assume any specific value more than another. Or maybe we assume it is symmetrical, You can then put maybe a truncated normal, so you stop between 0 and 1, but obviously you've shifted it. Or you can use the beta, which I'll go on about just now. Okay, so, and obviously if you don't have a 0 and 1 range, there's many other opportunities of other distributions. So, since it's a Bayes talk, I had to put in Bayes' theorem, otherwise I feel like I'm losing something. So, and this is my little picture. I'll claim this one. Okay, so it's not beautiful. It's what my poor third years have to be exposed to. One of them is here. Where is he hiding? Where's Peter? There he is. He's hiding. Okay, but he's not a third year now. He's way past it. But he was in my class, unfortunately for him. Right. But look, he's fine now. So this is a sample, your sample space S, and inside you've got subsets, however you want to define them. But what's important is it's a partition. So if you take the union of all of them, they make up the whole space, and they're obviously non-overlapping, right? Then if you want you have another set A which sort of fits over all of them, right? And you're interested in the probability of one of the B's given A, right? We'll do an example on the next slide. Then your Bayes' theorem gives you the probability of any one of the BRs given A. So you know A, but you don't know anything about the B's, according to this formula. So what's important is we might know A given each of the B's, but we don't know the other way around, B given the A. So that's what Bayes' theorem helps you do. So the bottom is obviously just a normalizing constant, and you take all of the possible numerators that go into there. So that's Bayes' theorem. I think everyone's sort of fine with Bayes' theorem. Okay. So I thought I must do an example, just because it's funny. So at the Indaba X, there are 100 mathematicians and 200 engineers and 1 statistician. Okay, 2, because Peter's here. But we'll take the statisticians out, and we'll just assume there's 300 people. How many people are there? Did they say anything? I wasn't here this morning. About 300? We'll just make an assumption. So let's say 60% of the mathematicians, so there are 100 mathematicians, so that's 60 out of 100. And 40% of the engineers, so 40% of 200, can apply Bayes' theorem correctly. Okay, I made up the numbers, okay, so please don't take offense. There was actually actuaries and economists in it, but I thought that's not very valid, so I changed it to these ones. Over lunch, you hear one of the delegates incorrectly apply Bayes' theorem. I'm sorry, okay. I wasn't at lunch, so it really can't be true. Okay? What is the probability the delegate is a mathematician? Okay, so I took some flack there, right? I'm sorry. So let's say B1 is the set of mathematicians, B2 is an engineer, and A is someone who can't apply Bayes' theorem. So we're interested in the probability that it's a mathematician given that they can't apply Bayes' theorem, right? So this is the formula because we just have 2 sets instead of 6 like the previous slide. So it's both of them at the bottom there. So the probability of not being able to apply Bayes' theorem given that you are a mathematician was 40%, because that's 60 can, right? 60% can, so it's the opposite. So it must be 1 minus 0.6, so that's a 0.4. The probability of it being a mathematician is 100 out of 300, right? And then this probability is then 0.6, because that's the positive, so it's 1 minus 0.4, and 200 out of 300 are there. And if you do the calculations, you get 25%. Okay, so that's not so, it's good for the mathematicians. Sorry, engineers. Right, so that's just an example in case because I think we did Bayes' theorem a long time ago. It's sometimes nice just to remember what we do and that we're still capable of doing it. All right, so now in Bayes' estimation, so now this is not just Bayes' theorem, now this is Bayes' estimation, so we're going back to this process, all right? There's a little proof, which my poor third years have to give to me very often in a test. But this is just to motivate, and I'm pretty sure you've all seen it, but I really wanted to put some mathematics in here. So the prior, by definition of conditional probability of marginal distributions, will be something like that, right? Then if you take this joint probability at the top, so that's a joint probability distribution of theta and the likelihood, right? Then you use conditional probability and you end it up like that. And this f of x is actually just the marginal of the joint. And we just drop it out because it's only there to make sure that the integral of this prior integrates to 1. Sorry, this is not the prior, this is the posterior, that terrible notation. I'm going to blame that on a 10 p.m. slide. So this should be theta given x. Right. So it's proportional to the likelihood. So that's the probability of observing this data, the x underscore, given the parameter times the prior, and then there's your posterior distribution. Okay. So the common coin flipping example, we want to determine the probability of observing heads. Okay, and let's pretend that we don't know that it's a non-biased coin. So we would assume it would be theta equal to 0.5, but let's say we're not going to make any certain assumptions. But we're now going to use Bayesian estimation, and we have a series of different values for the prior distribution. Right? Instead of just believing that we should see that come out of classical estimation, we make a series of options. And this 2, 3, and 4 are my 3 possible options. Not the only options, possible options. So number 1, you could say something very, very simple, like let theta equal to maybe theta is 0.5 or 0.7. Okay? Maybe someone told you something about this coin and you thought that could be a possibility. Okay, we obviously don't just make up priors, we think about what we've seen from our data. But I just made an example here. So it could be 0.5 or 0.7 with equal probability. Okay, so that's a discrete prior. Right? Or we could make it uniform, so we're not going to say anything about where it could be. It can be completely biased, completely unbiased, whatever you want. Right? Or an alternative, you use the beta. So the beta is a very flexible distribution over the interval 0, 1, okay, and it's used a lot. So, and then suppose we have the following observed data. We toss it, and we see 3 tails out of 10 tosses. Okay, so we immediately like, yeah, we think it's going to be biased, right? But we usually, okay, obviously in practice you're not going to do this, but usually you assume the prior before you observe the X data, right? But I mean, if you've seen that, then you would go back and update your prior, logically. But let's just assume those priors. So so my likelihood in this case with the coin flopping is a Bernoulli distribution with parameter theta. So if you observe a 1, then it's a heads. Okay, so your likelihood, and let's just at first look at the uniform, right? I've got a specific reason why I'm doing the uniform and the beta, you'll see just now. So let's assume we don't make any assumptions, we just know it's somewhere between 0 and 1. That's what you're doing when you make it a uniform prior, right? So your likelihood is just the product of all the individual fxi's, which are each Bernoulli, right? So Bernoulli looks like that. And if you proportion out, obviously we proportion out anything that doesn't have theta in it, okay? Because we're trying to find a distribution for theta. Anything in this which doesn't have a theta term in it is only there to make sure it integrates to 1. Right? So it's not going to change our final form of our posterior, so we can just chuck it out, right? But you make sure you don't chuck out the actual component. So there's a theta there and there's thetas there, so you don't chuck them out. But you can, doesn't matter, even though this is a product, there's never going to be a theta there, so it's fine, right? And it's a constant because remember you've got each of the xi's because they're observed. So you end up with theta to the sum of the xi's and 1 minus theta and then 10 minus the sum of xi's. This 10 my students often forget it. They just leave it as a 1, just as a side note. Anyway, so don't do that. So our formula is posterior proportional to likelihood times prior. So there's my likelihood. For the uniform, the prior is like that. So it's just 1, it just appears, right? So it's very uninformative. We call that an uninformative prior. It's added nothing to this formula, right? But even if you look at it, you can see you've made no hard decisions here. You just know it's between 0 and 1, and then you're letting the maths do everything for you, right? So if you look at this now, this is exactly actually a beta distribution, because now remember the parameter is theta, not x. Okay, here in the Bernoulli the parameter was x, right? So even though they look the same, they're different distributions because the random variable is theta. And I just put the beta PDF there in case, because we don't all know it off by heart. I don't, certainly. And this is obviously just your constant to make sure it integrates to 1, so it's proportional to that. So you can see those two things are similar. Remember, x is the random variable, theta is the random variable. So here you've got a minus 1, so this must be theta xi plus 1 to be the parameter. Okay, and remember the sum of the x's was 3 out of 10, so it was 7. 3 out of 10 tails. We're counting heads here, so it's 7 plus 1 is 8. And then the b parameter is 10 minus sum of xi also plus 1 to make sure that minus 1 works. And then it's 10 minus 7 plus 1, which is 4. So we have a beta 8, 4. Right. So we came from a Bernoulli. We assumed nothing about the prior except a range, basically. And it falls out that the posterior must be a type of beta. Okay? And note the range for the beta is 0, 1. So that's good, because we know theta has to be between 0 and 1. If we suddenly got a distribution that wasn't, then we've really made some silly error somewhere. So you've got to make sure that all of these things are okay. And there's the beta 8,4. Right, so remember that when we first did it, the uniform was this little square, right? That was our prior, so we made no informed decision. It was very uninformative. All we used was actually the information that we observed 3 out of 10 tails, so 7 out of 10 heads, and the maximum point of this distribution is sort of around 0.7. Okay, so it's bringing in our information, but it didn't tell us theta hat is equal to 0.7, not yet, right? It gave us a whole range of what we think it could be, which are most likely, etc., much more informative, right? The next step in estimation, which I'm not doing here because that's not our aim, is just to get the distribution, would be to say, okay, what do I expect theta to be? Okay, and there's various techniques for that. You choose a loss function and then you do various calculations. So under various loss functions, you could choose the mean of this beta, the mode, the median, etc. Okay, there's lots of alternatives and you can motivate which one's better based on what your situation is. But obviously if you take the mean, you'll see you're going to get 0.7, as you would like, as you would expect. So it works very nicely. What now, however, then I just plotted, before I go on, the other things that beta looks like and why it's so versatile. So if you put in a parameter 1, 1, it's in fact the uniform distribution. So actually, if we go back here, we did assume a beta there and we got a beta out. Just didn't know it, right? And when you have this situation, if you put in a beta there and you get out a beta, we call that a conjugate prior. They have the same form of prior and posterior. Right? The normal distribution does a similar thing, obviously. That's why people like it. But the beta obviously has much more versatility than the normal distribution. And it's got a truncated range, okay, which is not always the case for a parameter of a distribution, but in deep learning that's going to be most often the case as well. If you plot a beta 1, 2, it has an interesting little triangular distribution. Beta 2, 1 flips over. I mean, you wouldn't think of this as a distribution, but there's the beta doing it for you. Beta 2, 11, so a nice non-symmetric distribution towards 0. So if you believed, say you observed 3 out of 10 heads instead of 3 out of 10 tails, but you knew that and then you chose your prior based on that, you might choose something like this, but maybe a little bit more centered over 0.3. You can fiddle with it. If you increase, so that's from 11 to 100, it gets more and more closer to 0. 10, 1. Okay, now you see it becomes like an asymptotic distribution. Okay, so it's you're going to have problems with the mathematics here, trying to get the maximum and all of those sort of things. But still fine. If you increase the first parameter, it gets even more squished there towards 1. And if you take the 10, 10, I just chose 10 randomly, it starts sort of looking like it could be something normal. Okay, it's not, obviously, because it's 0 and 1, but it's nice and symmetrical. So if you really believe, so if you want to, from the beginning, and you can see I on purpose put it on 0.5, if you really hadn't seen that observed data and that was really only going to come later on, or you didn't know what would come out of the observed data, and you wanted to say, well, I know it might be biased, but let's just assume that we go from the middle, and then we sort of decrease away from it. Then this could be possible. And obviously, you could make it more squished up as you like. Okay, so it's very nice and versatile. So if we take this one, because this one seems like a good choice, and we do the same example, but with a beta 10, 10, our likelihood is still the same. Now I plug in my prior there, so that's the beta 10, 10 distribution, but note the theta is now a random variable everywhere. I get now a beta, using the same mathematics, a beta 17, 13, right? And if you plot it, it looks like that. So it's still symmetrical. It hasn't broken the symmetry, right? And it's more sitting over, see, so it doesn't quite capture it because we're only over 0.6. And observed data was the 7 over 10. Okay, so that was maybe not a good choice for the prior, but it's still got the symmetry going through there. Okay, so depending on what you want to assume about the parameters, you can choose different distributions. And it's very versatile. So in neural networks where you have many, many weights, and you'd like to maybe assume beta everywhere instead of a beta and a normal and whatever, then this could be a nice distribution with different parameters. It can capture all the uncertainty and all the different weights in different ways. Right. Not the only distribution, just one example. Okay. Right, the normal prior. Why do you think I don't like the normal distribution? It's beautiful. It's got beautiful mathematics. We have tables for it. We get nice estimation formulas. It's a lovely distribution, right? Except its range is from minus infinity to infinity. That's a big range. Right? So, and the normal 0, 1 obviously fits over 0, meaning that half of the values, the probability of them being negative. Right? So there's high probabilities, 50% of them are of it being negative. Okay? And you could obviously have a model where that would be useful, right? But not always. So the module that I teach where I teach this is actuarial statistics, and obviously they're applied into claims data. Okay? There's no way you're going to have a negative claim, right? So my famous question in the test, that I'm sure I asked Peter when he was in third year, was how would you justify the use of the normal distribution for claims data, right? This can't be used. That's terrible. Okay? It's telling you that the average value of a claim is 0, and I can have a lot of them that are negative. The highest is like over here. I mean, that's crazy. So obviously we transform it. If you make it very, very small, so the variance very, very small, you start zoning in on 0. Still bad, but we're making the variance small. But now if we shift it so that it sits over 10, and still within a sigma of 1, you can see that the probability of a 0 value, it's not 0, right? Yeah, if I zoomed in, you would see it. It's not 0. So this is not on the x-axis, but it's negligible, right? So you justify the use of the normal distribution because you shift it, but in addition to shifting it, you make sure that the variance is small. Yeah. Yeah, so they do log normal as well, but a lot of applications take the normal distribution, especially in this Bayesian type of estimation. But log normal is the most common way to go with financial data. Yeah. So you shift it so that it's closer to your mean value. So if you think your average claim is going to be 500 Rand, then you would make that 500. But then you also want the variance to be small. Okay, and variance, I feel, is often a forgotten parameter in our distributions. We're just like, oh, the variance is whatever, all right? But it's very important. It illustrates how confident you are in that data. If there's a high variance, there's something going wrong, right? So if you have a small variance, it means that you've, especially in insurance, you've pooled your clients together that are similar, right? And that's what you normally do in insurance. So these type of policyholders get billed this sort of premium because they're similar. So we can model them in a similar way. And this pool in a certain way, gosh, goodness gracious, I'll be fine, it's okay. So the variance must be very small. So as long as your variance is small, then you know that the part that's negative will be negligible. Right? So using the normal distribution is not bad, except that it's symmetric, okay? And you can't break its symmetry. That's it, that's its property. So if you believe that it's symmetric, then no problem, because you can shift it and figure out an appropriate variance. But if you believe it's not symmetric, then you really must be going for other types of distributions. Okay, so my key piece of information here is don't always go for the normal distribution. Okay, just because we feel comfortable with it, there are so many distributions, there's so many opportunities, go for other distributions. Okay, even if they are difficult to calculate, because computers nowadays have very fancy ways of helping you with that. Okay, so here's an example where I made it 10, I just increased the variance a bit, but you can see from 0, that part is very, very small. So that's still okay. Still a good distribution to use. Not the best, a good one. So a lot of the time, you can't calculate that likelihood easy or even get a nice closed form for the posterior, right? And I think years ago, that was a massive issue for people because we didn't have computers and we had to do everything by hand. And obviously, you could do these computational ideas by hand, but, you know, we only have so many hours in a day. But now we have computers, and life is much better. So if you can't get a nice closed form, really not a problem. So this approximate Bayes computation, I'm pretty sure they chose it specifically so that it's spelled ABC. It's called ABC, so if you Google ABC with stats, you'll get that out. I know that I think there's a package in R that does this sort of thing. So if you can't do that likelihood easily, or that likelihood is costly, then this is something you could use. And it gives you a sample of the posterior. So it doesn't give you a closed form, it gives you a sample. But if you have a sample, it's almost basically like a distribution. You can plot it, you can see what it looks like, you can still work out expected value, variances, all of those sort of things. You just don't have a theoretical formula, right? And obviously you can do it to whatever level of accuracy you want. Okay? shuffling with computation power. And I think it was Rubin, who's quite a famous statistician, who said this allows for a wider range of model choices. So you don't actually have to put a functional form onto that likelihood. You can put data in there and do things like that. So you're really opening up the forest of ideas here and possibilities. Okay, the other one is the MCMC, which I'm sure you all heard from, Markov chain Monte Carlo. So you sample from the posterior distribution. So again, you can't get a functional form, but you know what's going on before there. And you construct a Markov chain. How many people know something about Markov chain? Okay. So that's not so bad. So Markov chain, as you let it go on, it gets to an equilibrium, and you sort of get a desired distribution at equilibrium, and then you can sample from that. Okay, but Markov chain is quite nice and efficient because it's discrete. And then you sample after a significant number of steps. So obviously, if you go to infinity, you get the exact equilibrium distribution, and we can't in reality do that, but so you just let it go on until you think it's enough. Okay, and the Gibbs sampler is one of those. Okay, and just to illustrate my emphasis on the variation over distribution, last joke. Okay. I don't have to explain it, hey? It's fine. And that's my talk. Thank you very much. Yes. To the normal distribution. So I only showed you the beta and the normal, but only the beta because it's got that range 0 to 1. But you've got even the gamma. The gamma is obviously from 0 to infinity. But you can shift all distributions. I mean, just because the basic functional form has a range from 0 to infinity, you can just shift it. You can also truncate the normal distribution. You know your parameter can't go minus infinity to infinity, so you can truncate it. That's a possibility. But I think the biggest drawback of the normal distribution is the symmetry. Okay, I mean, to see symmetry in nature it's there, but it's not always going to be the case. And you might not have data that you can check that is symmetric. So now you place that symmetric assumption onto your weights in your neural network, but you don't actually know if it should be symmetric. Whereas if you choose something like the beta, it will blend into your data a bit better, for example. Oh, is that okay? What else? Yes? I think so. I'm not a Bayes expert, but I've got a number of colleagues in my department that are, and there are a number of uninformative priors that have a little bit more information. The one is called the Jeffries prior. Have you heard of that before? So I quickly looked up. I didn't put it on here because then I thought I'm really going to throw you under the bus. But the Jeffries prior maximizes the Fisher's information criterion or something. So it chooses a prior based on something also in your data. So there's very clever ways of doing it as well. Instead of just choose a range and then a shape, there's other much more clever ways to do it. Yeah, but so then I would look. Expert knowledge in statistics is always useful. You never discard what someone says. So if they believe that, you obviously question it and you say, do you say that because one person said it, or is it because you always see it in models, or But you have to take those things into account. We can't always be purely. This is what the math says. This is what I'm doing. You have to blend everything together. I think so. And the normal distribution for me is very restrictive. Not bad, but restrictive. That's my key. Yeah. So R is, at the moment, the big statistics software. Obviously, SAS is the biggest statistical software, but it's very expensive, and it's with black box. So R is very good at the moment, but I definitely wouldn't put Python behind R, because Python's got all the other advantages. I don't. No, I'm not. I can sit with you and advise you, but I don't know them offhand. No. Yeah.
You mentioned that using Bayesian parameter estimation, neural networks are more robust to overfitting. Can you explain that? Essentially, to make inference, you're going to have to estimate one value for the parameters in the neural network.
So I'm not a neural network expert, and I really can't answer that question. I apologize.
One more question.
Yes.
Do you have any idea how Bayesian parameter estimation scales when using neural networks?
So I think one of the things with these computational techniques allows for more scalability. That's one of the, I didn't put it there, but I remember seeing something like that.
Basically, just sample.
Yes, exactly. Yes. And then you can do it however you need, whatever your situation is. Yeah, definitely. Yeah. And even if you have a functional form like the beta-beta example, you can just still go Bayes computational and for the scalable situation. Yeah.
You had a slide where you had some like Bayesian deep learning website.
Yeah. Actually, the first thing that pops up, yeah, it's way at the beginning. If you Google Bayesian deep learning, yeah, there. It's a workshop that was at NIPS last year. Yeah. I think they have, at that link, they've got some videos and stuff from the workshop, so it could be quite nice. Yeah. Okay. Prior. Yeah, that's exactly right. Yes, yeah. Not always the case. Some cases, yes. The normal distribution, there's an example, I should have put that one up as well, that does it, but not always the case, no.
But even if it is the case, then it still makes sense.
Yeah, it justifies the use of, well, so maximum likelihood is one that people use often, obviously, and it does give the same value in some cases, but you don't just have that estimate, you have the whole distribution. So it's exactly, yes. Yeah. Please do it. Yeah. Yes. Yes. No, that's, yes. That's actually I should have thought about putting that in as well. So the tails of the normal are very low, right? And they're very shallow, and there's other better distributions, like the Weibull distribution, other distributions which lift the tails as well. So because it's quite restrictive from its mean to its sort of 3 sigma range. That's a very good point. Thank you for making that statement. I think it helps everyone as well.